Assignment problem. Introduction. We have studied transportation problem in previous lectures. Transportation problem refers to allocating resources, machines, materials, capital, etc. in a best possible way so that the costs are minimized or profits are maximized. The assignment problem is the special case of transportation problem, in which the objective is to assign a number of origins to the equal number of destination at a minimum cost, minimum time or maximum profit. Let us understand basic difference between transportation and assignment problem. Transportation problem. This problem contains specific demand and requirement in columns and rows. Assignment problem. The demand and requirement in each column or row is 1. Transportation problem. The number of rows may not be equal to the number of columns. Assignment problem. It is a square matrix. The number of rows must be equal to the number of columns. Transportation problem. There is no restriction in the number of allotments in any row or column. Assignment problem. There should be only one allotment in each row and each column. General form of assignment problem. Consider a general assignment problem consisting of n origins or sources O1, O2 up to On and n destinations or sinks D1, D2 up to Dn. Let the cost or time for associating ith origin to the jth destination is Cij. The cost matrix can be shown as follows. You can see over here there are n origins O1, O2 up to On with a supply each of 1. Destinations D1, D2 up to Dn with the requirements each of 1. C11 represents the cost of association between O1 and D1. C12 is the cost of association between O1 and D2 and so on. The whole cost is given to you. Let the amount of commodity supplied from I to j be denoted by Xij. Here Xij is defined as Xij equal to 1 if the ith origin is associated to the jth destination. Xij is equal to 0 if the ith origin is not associated to the jth destination. Note: if the number of rows is equal to the number of columns, then it is called a balanced assignment problem. If the number of rows is not equal to the number of columns, then it is called an unbalanced assignment problem. Now, the Hungarian method is used to solve this assignment problem. The following steps are followed to a given n cross n cost matrix to find an optimal assignment. Step 1. Subtract the smallest element in each row from all the elements of its row. Step 2. Subtract the smallest element in each column from all the elements of its column. Step 3. Draw lines through appropriate rows and columns so that all 0 elements of cost matrix are covered and the minimum number of such lines is used. Step 4. Test for optimality. First point, if the minimum number of covering lines is n, an optimum assignment of 0 is possible and we are finished. 2. If the minimum number of covering lines is less than n, an optimum assignment of zeros is not yet possible. In that case, proceed to step 5. Step 5. Determine the smallest element not covered by any line. Subtract this element from each uncovered elements and then add it to each elements where lines intersect. Then return to step 3. Let us understand the Hungarian method with an example. Suppose you work as a sales manager for a toy manufacturer and you currently have 3 salespersons located in different cities, say A, B and C. You want them to travel to 3 other cities D, E and F. The table below shows the cost in rupees of bus tickets between the cities they are located and the cities they have to travel. This is the matrix that is given to you. A, B, C are the places there where they are situated. D, E and F the places or the cities where they have to transfer. 250 denotes the cost of transportation from A to D. 400 is the cost of transportation from A to E, and so on. The whole cost matrix is given to you. Question is, where should you send each of your salesperson in order to minimize bus ticket fare? Solution. We shall solve this problem using Hungarian method. Step 1. Subtract minimal element from all elements of that row. Now you can see in this table that for the first row 250 is a minimum element, for row 2 350 is a minimum element, and for row 3 200 is a minimal element. So subtract 250 from all elements of first row, 350 from all elements of second row, and 200 from all elements of third row. So we get a new table. 250 minus 250 is equal to 0, 400 minus 250 is equal to 150, 350 minus 250 is equal to 100. So that gives you the first row. The second row, we have to subtract 350. So 400 minus 350 is equal to 50. 600 minus 350 is equal to 250. 350 minus 350 is 0. And for the third row, we have to subtract 200. So we'll have the third row as 200 minus 200 equal to 0. 400 minus 200 equal to 200. And 250 minus 200 is equal to 50. Step 2. Subtract minimal element from all elements of that column in the resultant matrix. So the table below is the resultant matrix that we have derived from step 1. Now we have to select the minimum element from each column. So in the first column, minimal element is 0. Second column, the minimal element is 150. And in the third column, the minimum element is 0. So subtract 0 from all elements of the first column, 150 from all elements of second column, and 0 from all elements of the third column. So we get a new table. Column wise, if I say 0 minus 0 is equal to 0, 50 minus 0 is equal to 50, 0 minus 0 is equal to 0, that gives you the first column. Second column now, we have to subtract 150. So 150 minus 150 is 0, 250 minus 150 is 100, 200 minus 150 is 50. And the last column, we have to subtract 0. So 100 minus 0 is 100, 0 minus 0 is 0, 50 minus 0 is 50. Step 3, the important step. Cover all zeros of the matrix with minimum number of horizontal or vertical lines. In the below table, you can see that at least 3 lines are required to cover all zeros. So minimum number of lines is equal to number of rows, because you can see there are 3 rows A, B and C. As the number of minimum lines is equal to number of rows, optimal solution can be obtained. Step 4. Assign to zeros. This is an important step that we have to take care of. First row has 2 zeros, second row has 1 zero, and third row has 1 zero. So starting with first row, there are 2 zeros, so we cannot assign to it. Second row, there is only 1 zero, so we'll assign to that 0, and any other 0 in that row or a column will be cancelled. Again, coming back to row 1, there are 2 zeros, so we cannot assign to that. Row 2 is already assigned. Row 3 now has only 1 zero, so we will assign to this. When we assign to this, any other 0 in that row or column will be cancelled. So cell 1 1, the 0 in cell 1 1 will be cancelled. Now you can see in row 1 only 1 0 is left. So assigning to row 1. So here row 1 now has an assignment. So cell 1 2 is assigned, cell 2 3 is assigned, and cell 3 1 is assigned. Here the same assignment made to the original cost matrix. That means the position that we have assigned in step 4 is placed into the original table. So A to E 400, B to F 350, and C to D 200. Thus, final allocation and corresponding allocation cost is tabulated below. Salesman from city A to city E cost 400 rupees. Salesman from city B to city F cost 350 rupees. Salesman from city C to city D 200 rupees. So total allocation cost comes to 950 rupees. Let us take another example. In a factory, 3 jobs are to be assigned to 3 machines. The time in hours taken by machine to complete the assigned job is given by the below matrix. Assign the jobs to the machine in such a way that the total time taken is minimum. This is the table that is given to you. This shows that if job 1 is assigned to machine 1, 19 hours are taken. If job 1 is assigned to machine 2, 28 hours are taken, and so on. The whole matrix is given. Solution. We shall solve this problem using Hungarian method. Step 1. Subtract minimal element from all elements of that row. You can see in the below table, from the first row, that is 19, 28 and 31, minimal element is 19. Second row, the elements are 11, 17 and 16. So, minimal element is 11. Row 3, 12, 15 and 13, minimum element is 12. So, subtract 19 from all elements of first row, 11 from all elements of second row and 12 from all elements of third row. So, the new table that we get, row wise, 19 minus 19 0, 28 minus 19 is 9, 31 minus 19 is 12. Row 2 we have to subtract 11, so 11 minus 11 0, 17 minus 11 6, 16 minus 11 is 5. Row 3 we have to subtract 12, so 12 minus 12 is 0, 15 minus 12 comes to 3 and 13 minus 12 comes to 1. Step 2. Subtract minimal element from all elements of that column in the resultant matrix. Resultant matrix means the matrix derived in step 1. So, the table below gives us the resultant matrix of step 1. First column, the minimum element is 0. Second column, the minimal element is 3. And the third column, the minimal element is 1. So, subtract 0 from all elements of first column, 3 from all elements of second column and 1 from all elements of the third column. So, the new table that we get is column wise, 0 minus 0 is 0, 0 minus 0 is 0 and 0 minus 0 is 0. Second column, we have to subtract 3. So, 9 minus 3 is 6, 6 minus 3 is 3, 3 minus 3 is 0. And the last column, 12 minus 1 is 11, 5 minus 1 is 4, 1 minus 1 is 0. Step 3. Cover all zeros of the matrix with minimum number of horizontal or vertical lines. Now, here the interesting point is that we can cover all zeros with only 2 lines. So, number of lines is 2 and the number of rows is 3. Number of rows you can see there are 3 jobs, 1, 2 and 3. So, there are 3 rows. So, as the number of lines is less than number of rows, optimal assignment of zeros is yet not possible. So, we will have to do one more step before going to step 4. The smallest element not covered by any line is 3. Subtract 3 from each uncovered elements and then add it to each elements where lines intersect. Doing this procedure, we get a new table which is given below. We shall again cover all zeros with minimum number of lines. Now, you can see in this resultant matrix at least 3 lines are required to cover all zeros. So, now we have number of lines is equal to 3, number of rows is equal to 3. So, as number of lines is equal to number of rows, optimal assignment of zeros is now possible. So, we now move on to step 4, assign to zeros. First row, there is only one 0, so we will assign to that 0. But any other 0 in that row or column is to be cancelled. So, 0 in cell 2-1 will be cancelled. Now, in row 2 only one 0 is left out. So, we will assign to that 0. Again, any other 0 in that row or column is cancelled. So, 0 in cell 3-2 is cancelled. Now, row 3 has only one 0. So, we will assign to that. Here, the same assignment is made to the original cost matrix. So, now we have job 1, machine 1, job 2, machine 2 and job 3, machine 3. The assignments are made in the original table. Thus, final allocation and corresponding time is tabulated below. So, job 1 is to be assigned to machine 1 and 19 hours will be taken for it. Job 2 should be assigned to machine 2 and 17 hours are required. Job 3 to machine 3 and 13 hours are required. So, total allocation time will be 49 hours. One more example. In a workshop, there are 4 mechanics and 5 jobs. Time taken to complete each job is given below. Solve this assignment problem. So, you can see the 4 mechanics are given and there are 5 jobs 1, 2, 3, 4 and 5. 9 represents that if job 1 is allocated to mechanic A, the time taken, that is 9 hours, are given to you, and so on. The whole matrix is given. Solution. In this assignment problem, there are 4 rows and 5 columns. So, number of rows is not equal to number of columns. So, it is an unbalanced assignment problem. Here, there is one less number of row compared to number of column. To convert it into a balanced assignment problem, we shall add a dummy row with 0 cost. So, we are adding a dummy row. This gives us a balanced assignment problem. We shall solve this problem using Hungarian method. Step 1. Subtract minimal element from all elements of that row. So, you can see the first row, the elements are 9, 6, 5, 4 and 2. So, the minimum is 2. Similarly, for row 2, the minimum element is 2. For row 3, the minimum is 3. For row 4, the minimum element is 2. And for the dummy, obviously, it is 0. So, subtracting 2 from all the elements of the first row, 2 from all elements of second row, 3 from all elements of third row, 2 from all elements of fourth row and 0 from all elements of the fifth row. So, we get a new table that is given below. Step 2. Subtract minimal elements from all elements of that column in the resultant matrix. This is the resultant matrix of step 1. Now, you can see in column 1, the elements are 7, 5, 3, 0 and 0. So, minimum is 0. Similarly, for column 2, minimum is 0. Column 3, column 4, column 5, all have minimum element 0. So, subtracting 0 from all the elements of columns, and we get new table that is given below. Step 3. Cover all zeros of the matrix with minimum number of horizontal or vertical lines. Now, if you look at it carefully, 4 lines can cover all zeros. So, number of lines are 4, but number of rows including the dummy, they are 5. As number of lines less than number of rows, optimal assignment of zeros is yet not possible. So, what to do now? Subtract or identify the smallest element not covered by any line, which is 1 now. Subtract 1 from each uncovered elements and then add it to each elements where lines intersect, and we get this new table. We shall again cover all zeros with minimum number of lines. Now, you can see in this resultant table, at least 5 lines will be required to cover all zeros. So, number of lines is 5, number of rows is 5. So, as the number of lines is equal to number of rows, optimal assignment of zeros is now possible. So, we will move on to step 4, that is assign to zeros. First row has only 1 0, so we will assign to that 0. But again, we have to take care any other 0 in that row or a column will be cancelled. So, 0 in cell 3, 5 will be cancelled. Now, in second row only 1 0 is there. So, assigning to that 0. Now, any other 0 in that row or a column will be cancelled. So, 0 in cell 5, 4 will be cancelled. Now, assigning to 0 in the third row. So, when we assign to 0 in that row, 0 in cell 5, 3 will be cancelled. Now, there is only 1 0 left in row 4. So, assigning to that. When we assign to that 0, 0 of cell 5, 1 will be cancelled. And now, in the last row, only 1 0 is left out, which is in cell 5, 2. So, we will assign to that 0. Here is the same assignment made to the original cost matrix. So this is the table that we originally had in the question. According to the positions that we get in step 4, we have assigned in this table. Thus, final allocation and corresponding time is tabulated below. So mechanic A should be assigned job 5 and 2 hours are required. Mechanic B to job 4, 2 hours are required. Mechanic C to job 3, 4 hours will be required. And mechanic D to job 1, 2 hours are required. So total allocation will be 10 hours. Here it is important to note that job 2 is assigned to a dummy mechanic, and so job 2 will remain unattended. Let us summarize the whole assignment problem. The assignment problem is a special case of the transportation problem in which the objective is to assign a number of origins to the equal number of destinations at a minimum cost, minimum time or maximum profit. It is a square matrix. The number of rows must be equal to the number of columns. The demand and requirement in each column or row is 1. There should be only one allotment in each row and each column. The general form of assignment problem. The cost matrix can be shown as follows. There are n number of origins O1, O2 up to On, each having supply of 1 unit. N number of destinations D1, D2 up to Dn, each having 1 unit of requirement. C11 represents the cost of association of O1 and D1. C12 is the cost of association of origin 1 and destination 2, and so on. The whole cost matrix is given. Here Xij is the amount of commodity supplied from I to j and defined as Xij equal to 1 if the ith origin is associated to the jth destination. Xij equal to 0 if the ith origin is not associated to the jth destination. If the number of rows is equal to the number of columns, then it is called a balanced assignment problem. But if the number of rows is not equal to the number of columns, then it is called an unbalanced assignment problem. Unbalanced problem is converted into balanced assignment problem by adding a dummy row or a column. Thank you.